and we're here with Analog Devices having a conversation with Rene Kahr. And Rene Kahr can explain what it takes to develop a signal generator on a chip and overcome all the typical issues you're having if you want to create a generator up to 9 gigahertz, I think, right?
Exactly.
So what exactly do we have on the table here?
Well, we have what we're calling a vector signal generator, which is a DAC and the output buffer all on one chip and one laminate. And this overcomes a lot of the application issues that you normally would have. Impedance matching, elimination of bail-in and capacitors. So basically you take this chip, you drive right out to an SMA connector, you maintain the 50 ohm impedance, and you're done. And that gives a lot of capability. This is a 2 or 3 month exercise for a lot of customers, so we're saving that time.
Yeah.
And we're also providing great wideband performance.
Okay.
So you can take 2.25 gigahertz signal, place that anywhere in the spectrum up to 9 gigahertz, get very good flatness up to about 6 gigahertz. And this is ideal for signal generators, radar applications, and all types of test instrumentation that you might like.
Yeah. You're making the life of a RF design very easy with that.
That's part of our mission at ADI, is not just to provide components, but solutions. And so we do that in a number of ways, different form factors, but a lot of the ways is to provide more of the solution for busy engineers who can copy and paste and move on to where they really add value, which is often in a different part of the system.
Yeah, a lot of RF engineers are familiar with the issues you mentioned, the change in impedance. If you do RF design, you have to overcome a lot of difficulties. What is the key success factor in this design? What have you brought in to overcome these issues?
Well, it's really the impedance and output level match across the wide bandwidth that this part operates.
Yeah.
So normally, you would have to compromise in terms of where you get the best performance, where you get the best impedance match as you roll across the frequency. But with this part, that compromise has already been dialed in, and you've got the best possible performance without having to do days of simulation and test fitting different op amps, all that kind of thing. So we've kind of really done that hardcore RF engineering for you, so you don't have to.
Sounds excellent to me. You have it on display here, the actual generator, the actual RF generator.
This is the generator here, and so this is hooked up to our ADS7 eval platform, and this uses a clock from our 4371 clock generator. And this here is the little bit of a fan on the 9166, and we'll output this cable here. And if we look at the result, we're producing a 802.11ax signal of about 125 megahertz of bandwidth, and we're placing that up at about 5 gig. And you can see the resultant EVM measurements are impressive, about 10 dB better than required by the spec. And so we could, put the signal way up at 7, 8, 9 gigahertz, or do whatever else we want. But there's a lot of flexibility. And if you want a kind of a more modern form factor, we have it here with a Raspberry Pi shield. And so again, it's a pretty simple design from the 9166 out to the output SMA connector, but this is an example of a lower cost platform that might be more attractive to certain industries.